Thank you, Marge. Thank you, 2 Feet, for inviting me. I want to stress that everything that I say this morning is joint work with Mohammed Al Bahrawi uh, from the United Arab Emirates. So he and I have a number of papers on topics related to this, and I'm going to speak about one in particular this morning, but it will be explicitly on a generating function more special than the full generating function for two-color partitions. If you This topic really goes back to McMahon, and if you just look at partitions where the parts are of two colors, it's basically the generating function involved would in general would be the square of the generating function for ordinary partitions, and consequently, being a modular form, will have a rich development of arithmetic properties, and this has been treated, say, by a paper by Oliver Atkin. So the work that Bahrawi and I are dealing with this morning is rather more specialized. So we're going to consider partitions with parts of two colors, say red and blue, where the smallest part is blue and odd. So I've phrased this rather badly. There can be small red parts as well, but there always has to be a blue smallest part. And the smallest part does have to be odd, but you can have red smallest parts as well. And in addition, the requirement is that the even parts are distinct. So that means distinct either by either color or magnitude. So you can have a red 2 and a blue 2, for example, because they are distinct by color, but you can't no repeats of the same magnitude and same color. And by B of n, we will denote the number of such partitions of n. So here's an example. B of 4 equals 10. So the smallest part in each partition there has to be at least one blue part that's the smallest part. So you can see among the first 4 partitions here, the number of reds are increasing up to 3 reds and 1 blue, but we always have to have a blue part as smallest part. And if you work through, then you can see that these are these partitions where the smallest part is odd, the even parts are not repeated, and so in this case, B of 4 equals 10, and there are the 10 partitions listed on the screen. So we're going to use the standard Q series notation. So the first symbol A semicolon Q sub n is this Q Pochhammer symbol. So the classical hypergeometric series has the ordinary Pochhammer symbol, which would be A times A plus 1 times A plus 2 up to A plus n minus 1, product of n factors. Here, instead of that, you have 1 minus A, and the power of Q then increases from Q to the 0 to Q to the 1 up to Q to the n minus 1. Again, there are n factors, and we also want the infinite product, which is this limit as n tends to infinity is a q to n. For those of you who are devoted to formal power series without convergence conditions, you should ignore the last line here. The rest of you who view these things as analytic functions, the absolute value of q has to be less than 1 in order for there to be convergence. So here's the generating function for B of n. So you see that you have the infinite series the q to the 2n plus 1, that's designating this one blue summand that is odd. The product in the numerator provides us with the distinct parts that are even, and consequently, you can have a 2 red and a 2 blue, so you can have 2 repeated but with different colors, but the parts in effect must be distinct. The denominator factor gives you all the odd parts, and you can have multiple blues and reds, but the q to the 2n plus 1 in the numerator guarantees that the smallest part, blue part, appears. So, how should we go about studying this function? Well, let's begin with the power series expansion. So here's a copy of a page that's put out by Maxima. So most of you probably are using either Maple or Mathematica. So it takes someone as old as I am to be using the granddaddy of computer algebra packages, which is Maxima. So the top line, of course, is just defining the Q Pockhammer symbol, which is the product of 1 minus aq to the j. J runs from 0 to n minus 1. And this D2 line gives us then the Taylor series expansion of the B product out to M. This is not a very efficient thing. I don't really need great efficiency, but I could have trimmed all the products down instead of having them out to M. I could have taken them to the floor of M over 2, but I did not. So let's expand this series out to 41 terms. So what's the advantage of a power series expansion? Well, sometimes you get a lacunary series, but if this is almost the opposite of a lacunary series, the coefficients are obviously monotonically increasing. So we then look for arithmetic properties. And if you look at this, the first line, there are only 2 odd coefficients, that of q and q to the 5th. There are no odd coefficients in the second line. In the third line, q to the 13th. So lots of coefficients are even. So it's easy to make Maxima tell you where the odd coefficients are. Just divide the series by 2. And you see the odd coefficients of q, q to the 5th, q to the 13th, q to the 25th, q to the 41. Okay, so obviously there's something going on here. There's a very sparse appearance of odd coefficients. So indeed, here are the odd coefficients. So we can easily identify this sequence. It's obvious. It's not difficult at all to take differences and then second differences, which will show you that it's a quadratic sequence, but we can spot it even more easily as follows. Namely, one, just subtract 1 from each of these things, and you get a number that is divisible by 4. And so you have 4, 0, 4, 12, 24, 40. And so this is 4 times 0, 4 times 1, 4 times 3. So it's clear what this sequence is. It appears that B of n is even, except when n is 1 plus 4 times some triangular number. So how do we prove this? Well, the game is that mod 2 plus 1 is equal to minus 1. And so, consequently, it's possible to change signs of any term you want. And modulo 2, that is quite okay. So, mod 2, I take one factor in the numerator, one of those infinite products, and I drop the minus sign. And in the denominator, I take one of the infinite products and I add a minus sign. And so that this is congruent mod 2. And now, recalling the algebraic fact that 1 minus x times 1 plus x is equals 1 minus x squared, the numerator products combine together to give me this q to the 4n plus 4 on base q to the 4th, and the denominator products multiply together to give me q to the 4n plus 2 and q to the 4th. So I now have a simpler series. So now I do one of the standard devices in dealing with series like this. I extend the numerator product down from where it starts at q to the 4n plus 4 all the way down to q to the 4th, so that I have the full infinite product q to the 4th that I can factor out of the numerator. But then I have to cancel out from it the first n factors of that product, which then have to go in the denominator. So the q to the 4th infinity in the numerator divided by q to the 4th sub n in the denominator is the original numerator product that you see in the penultimate line here. And similarly with the denominator product, I bring out a full q squared q to the 4th infinity, and then I have to cancel out the first n terms of that product. Okay? So what we have here now is a set of these quotient of infinite products times this series, which is an instance of Cauchy's extension of the Q binomial theorem. So that's equal to this Q binomial theorem sums this to an infinite product. So now I have basically the same this infinite product. You can see it effectively squared. But if I've changed the sign in the second products with putting in minus sign, what do I get but this? Q to the mod 2, it again extends to that. And that is a special case of Gauss's triangular number series with Q replaced by Q to the 4th. So that's equal to that. And now we see that the assertion is true because the top line right up by proof is the generating function for b of n, and mod 2 it's congruent to this q times the summation n equals 0 of q to the 4 times n plus 1, and that establishes this result that b of n is even except when n is 1 plus 4 times q to the 4th. So next, we observe that B of Q has a natural foreshadow. What do I mean by a foreshadow? So this is a term that I invented when I was writing a short article in honor of Hansraj Gupta. This is perhaps one of my most obscure articles. It appears, I think, in the 4th volume of the collected works of Hansraj Gupta. It's a very simple idea. The foreshadow method relies on the simple observation that 1 minus x squared is congruent to 1 plus x squared mod 4. Okay, and more generally, if you have a power series in Z, if you square it, it's congruent to f of minus z squared mod 4. And this is fairly easy to see because if you take the difference of these two and factor it, the first component f of c plus f of minus c, that's twice the even part of f of c. And the second factor is twice the odd part of f of c. And consequently, you have a factor of 4 on the right-hand side. And so that f of c squared is congruent to f of minus c squared. So I define B4 of Q, where the only thing I do is to change the sign in the product in the numerator. So in the B of Q, that the product in the numerator has a minus sign in front of the Q to the 2n plus 2. Here it has, I have removed the minus sign. And so, obviously, now I can do the similar thing that I did with B of Q to B4. So again, we have a series to look at. I should have said, incidentally, that the previous series, one of the things that one automatically does when you get a new series like this, if you don't recognize it immediately, is to run off to the OEIS, the Online Encyclopedia of Integer Sequences, and the series for B of Q is not in the OEIS. But if I turn to the OEIS here, well, I suspect, given the way this shows up, none of you can read this. And so I will tell you what the top line says. It says that this sequence is the number of divisors of 2n minus 1. So, and as I suggest, this is basically unreadable. I'm sorry I didn't expand it, but if I'd expanded it, I would have cut off some lines. The thing that one hopes for also when you go to the OEIS is that you will wind up with the generating function. But if you look through the lines here, well, you do get sub things for the generating function, but no real explanation of it. You get a formula from Mathematica. So we do ask, what is the generating function for d of 2n minus 1? Well, we know the generating function for the number of divisors of n. It's just this famous Lambert series, so summation n equal 1 to infinity, q to the n over 1 minus q to the n. And the way to see that that's the number of divisors is just to expand the sum n in this series as a geometric series, and you will see that you'll just get sum over n greater than or equal to 1, sum over m greater than 1, q to the mn. And so the number of times you get a given exponent is the number of times you have divisors of n. So if we want the generating function for d2n minus 1, all we need to do is take the odd part of the generating function for d of n, which we have then written down in this third line in this first equation here. So if n is even, the terms cancel because those minus signs in the second sum disappear, and the second sum is identical with the first sum when n is even. So the only terms that are left are when n is odd. And you see that when n is odd, basically we get the intervening minus sign becomes a plus sign, and the minus sign in the denominator becomes plus. And you can now combine these two terms, obviously. And it turns out to be that. So we really want to change variable so that we, instead of having q to the 2n minus 1, we have q to the n. So basically, you replace q by q to the 1/2 and then multiply by q to the 1/2. And you wind up with this expression. So this is the generative function that we require. And in order to show that this B4 is actually equal to that generating function, we require the Heine transformation. So Heine was working in the middle of the 19th century, and he defined these series, as you see the definition at the bottom of the screen. Basically, this is the Q analog of the ordinary hypergeometric series, where in the ordinary hypergeometric series, you have the standard Pochhammer symbol. In the Q hypergeometric series, you have the Q Pochhammer symbol. And Heine showed that you can go through a variety of transformations of this series, the first one being the formula that you see in the middle of the screen. So this is the Q analog of the integral representation of the classical hypergeometric function. You don't see any integrals here, you just see two series. I won't go into detail, but basically the Q analog of the Riemann integral is basically another Q series, and if you work it out to set it up in terms of Q integrals, this formula of Heine is basically the Q analog of that integral representation. But this is necessary for our work here. So I want to show that B of Q, the generating function for B of n, is congruent to the generating function for D of 2n minus 1 mod 4. So the point is that I'm using this foreshadow, and which means that B of Q will be congruent to B4 of Q mod 4, and B4 of Q is this infinite series. And I want to show, what I'm going to show is that this series is actually equal to that divisor, the generating function for D of 2n minus 1. Okay? So the first thing to do is the same device that we did previously, namely bring out the generating functions. And unfortunately, I've lost a square. So in the infinite product out front, the denominator factor should be squared. Sorry about that. And once you factor those out, you are left with a 2phi1 of the type that you see there. So I seem to have left off the square again in this line. But anyway, the Heine transformation of the 2phi1 is valid. And if you did have the square by the denominator product, you would see that all these infinite products cancel, except for 1 minus q factor, which is canceled out of the series that you have for the 2phi1. And once you take all that, this slide is definitely has serious problems. Anyway, I've dropped that square all the way through, and in the bottom slide, that should be n greater than or equal to 1, and that is the required generating function, and that then proves this theorem that B of n mod 4 is congruent to the number of divisors of 2n minus 1. So the question remains, namely, can we learn anything fundamental about B of Q itself? So what we've done so far is to do congruences. We know basically the behavior of B of n mod 2 and mod 4, but we really don't know anything about this. Is there a representation of this generative function in terms of more classical, more fundamental series? So the first step is to get B of Q into classical hypergeometric form. All right, so here it is. This is the classic B of Q, and I have included all the squares this time, fortunately. And I've used the same device that I've used twice before, namely I've brought the infinite products with uh, out to the front and then left finite products inside so that I have this standard sort of Q series form. Now, this is not the classical R plus 1 phi R because there's no Q squared in the denominator. So I have to introduce it in both numerator and denominator, which brings me then to a 3 phi 2 that looks like this. So the question is, can I do anything with this Q hypergeometric series? So there are only two forms of a 3 phi 2 that appear in classical identities. For the 2 phi 1, the Heine transformation applies to a fully general 2 phi 1. You have A, B, C, and T. You have all the parameters are unrestricted. In a 3 phi 2, you will have 6 parameters, A, B, C, D, and E, and then the power series variable. And in full generality, there are not any classical nice identities. You require either this first type, where the power series variable is the product of the denominator parameters divided by the product of the numerator parameters. That's type 1. Or you have type 2, where the t variable is just q. So here are transformations of 3 phi 2 series. I hope you can read them. These are taken from the appendix of Gasper and Raman. The second, the last entry is not relevant for us because this q to the minus n means these are terminating series, and our series are non-terminating, so that we are only interested in the possibilities with maybe the top line. And here are either harder to read, but hard to put on the screen. We have further formulas that this 333 involves of type 1, but in 334 we have both types. The left-hand side is type 1, the right-hand side is type 2. Note that this 3 phi 2 of q only appears on the right in 334. All of the other 3 phi 2s are this form. Well, let's go back and look at this. If you take the product of the denominator parameters, it's q to the fourth. And you have the numerator parameters as q squared as well. So you're stuck. You don't have a type 1 here, but you do have a type 2 because, well, since the base of this 3 phi 2 is q squared, and the argument is q squared, so you basically have a type 2. So the only thing that's going to be useful for you is this 334. So one further observation that, to save time, I will put this massive thing on the screen without much motivation. Note also that their type 1 3 phi 2 also appears in the limiting form of Watson's Q analog of Whipple's theorem. So Watson's Q analog of Whipple's theorem is basically a terminating series equal to finite products times terminating series. If you let the integer variable tend to infinity in that identity, what you wind up is the thing that you see on the screen, where the I've condensed the notation a bit, uh, but I won't say too much about it because it's enough down in the weeds as it is, just to say that it will be useful later on. So that's our only possible approach to transforming B of Q is this 334. And so we consider, now you'll be able to read this. We consider 334, we replace Q by Q squared, and then we make these various substitutions so that we have this three-term identity of 3 phi 2's. And basically, the game is that the first 3 phi 2 on the right-hand side is precisely the 3 phi 2 that appears in B of Q. And so we can transform this nicely. So multiply both sides by sufficient infinite products to make this come out to be the right thing. And what you wind up with is both the 3 phi 2 on the left hand side and the 3 phi 2 on the right hand side that was B of Q, I've now multiplied through appropriately to get exactly B of Q. And the second term, the 3 phi 2 had a Q squared in the numerator, and so it collapses to this particular expression. And so I have two terms that involve Q hypergeometric series, and I have the B of Q. So I want to evaluate these terms, both T1 and T2. So apply the Heine transformation to T2, we find immediately that it comes out to be very much like the generating function for D of 2n minus 1. And so, whoops, I went the wrong direction. Sorry. Applying the limiting form of Watson's Q analog of Whipple's theorem to T1, we find that it's equal to this. And so we have the infinite products outside, but now we have the much more concise form. Namely, we have one of these Q Appel series, which is basically the Q Appel series is basically a series where you have Q to some quadratic exponent and then a rational function involving Q to the n, so that you now have T2 is a Lambert series, and T1 is a Q Appel series, so that we have reduced the B of Q then to these two more classical forms. So I have one last topic to consider here. So finally, Bahrawi and I considered a much more general case. So what is this more general case? So basically, K equals 1 is the original B. But what we are requiring here is that one of the types of parts that are odd do not start with 2n plus 2 when the smallest part is 2n plus 1. They start at 2n plus 2k, so that we are excluding certain even parts of one of the colors. And this, so we let bk, capital BK of n, be defined by this. And indeed, we're able to produce two congruences for k equal 2. So that means just the second case along, we are able to do another set of congruences for these particular partition functions. And I want to show you how this goes. So we like to, obviously, whenever you see mod 4, one wants to apply the foreshadow method. Well, the problem with applying the foreshadow method that we did in the original case is that the numerator is no longer a perfect square, but we increase it. We throw in the extra factor needed to make it a perfect square, and then put in the denominator the one term that is needed to cancel that out. And so now we have that as a perfect square. And so hence B2 is congruent to B bar 2 of Q mod 4, which is given by this expression where we have now eliminated the minus sign in the numerator because that factor is squared, and so we can leave it out. Obviously, you had two choices to make. You could either leave off the first factor, or you could put in a new first factor. What works best is the choice we've made here. So thus, B2 bar of Q is equal to this. And now take a look at this. Remember what type 1 3phi2s are. It's the product, the series variable, the power series variable, has to be the product of the denominator parameters divided by the product of the numerator parameters. The product of the denominator parameters is minus q to the sixth. The product of the numerator parameters is minus q to the fourth. The division of the denominator product divided by the numerator product is q squared. So we indeed have a type 1 as well as a type 2. But type 1 has many more things connected with it. And so this shows great promise. This is a type 1 3phi2. So we may apply the Watson that I showed you earlier with q by q squared, and then I've given the A, B, C, D, and E necessary to substitute. So here's B2 bar. After you apply a Watson, what you wind up with is the infinite products all cancel out, and you wind up with this sort of ultra Alpel-Lerch type series, which we want to simplify this a little bit. So I'm going to split off the first term and sum from n equal 1 to infinity. And I do some algebraic manipulation of things in order to, because I'm interested in working mod 4. And you see that what I've done here is to get two twos involved, so that the second term, the thing inside the big parentheses, that second term can immediately be dropped, because mod 4, it's 0. And so mod 4, I wind up with this series. And now I make some observations. Let's remember what I'm shooting for. I want to deal with 4n plus 2 and 4n plus 4. In other words, I'm looking at even coefficients. 4n plus 2 and 4n plus 4, those constitute the even coefficients. But take a look at this series. If I replace q by minus q, the denominator does not change, because the exponents on q are 2n or 2n plus 2, both of those are even, so the denominator doesn't change. N squared plus 3n, when you replace q by minus q, that doesn't change because that the n squared would change the sign as would the 3n, so that there are two changes of sign, but the q to the first power changes. So the infinite series is an odd function of q. That means the only even coefficients arise from this rational function outside. And so we need to determine the residue classes of from the rational function. But it's clear how those behave mod q to the fourth, because the denominator is 1 minus q to the fourth. So there is no, in this rational function, the q to the fourth power doesn't appear. So b2 of 4n is congruent to 0. And the 2 mod 4 appears with the coefficient of 2. So it's congruent to 2 mod 4. So one of the things that I promised in my abstract was a discussion of open problems, but I wrote that abstract many months ago, and in the interim, Bahrawi and I have basically treated the open problems, and indeed, what I will say that we're writing now a paper which is devoted to what are called corners, which are basically plain partitions with one row and one column. They're basically somehow the dual of these partitions with two colors. And many of the problems that I was going to talk about there have been solved by us. So all I can say is that I will be giving a talk on this at the regional meeting in Washington, D.C. of the American Mathematical Society in early October. So if you want to see a further extension of this, please join my talk in early October. And with that, I say thank you very much for your attention.